Hello everyone, welcome to watch this video. In this video, I'm gonna show you how we get Taylor series. And also I'm gonna show you two examples how we apply time series in a function. And then we're gonna revisit bound convexity. As you all know that bound convexity is derived from Taylor series. And I hope after you watch this video, you're gonna have a better understanding on Taylor series as well as bound convexity. So now I'm gonna share my screen. So first, I want to introduce what is Taylor series. Taylor series is a represent a function, for example, fx by a power series, and we can do approximation for any open interval CL and CU that contains C here. And what is a power series? For example, let's take C as Z as a variable of interest, Z0 plus Z1 plus Z to the power of 2 and keep going, plus Z to the power of n. This is called a power series. And if our variable of interest is y here, y0 plus y1 plus y2 plus ym, y to the power of m, that is also a power series. And because some function can be very complicated, and when we want to do approximation, we may want a simpler format, such as a power series. So in this case, we want to represent the function, for example, function fx into a power series, and the z and y here is x minus c in our function function power series here. And the problem is that this a0, a1, a2, an, those coefficients are unknown. So then we found that a0 equals to fc. So we just imply c in the function f, that is a0. a1 is the first order derivative of function f with respect to x at x equal to c. And a2 is the second order derivative of function fx with respect to x at x equal to c divided by factorial of 2. And keep going. And then we can plug those coefficients into our power series, and what we get is here. This is called Taylor series. In this video, I'm going to show you how we get Taylor series. Two examples to show how we apply Taylor series, and then we will revisit the bound convexity in our lecture. And I will touch the surface that why the Taylor series is so important. So first, this is the original power series with unknown coefficients. And we label this equation as equation 1. And our purpose is that we need to find out coefficients a0, a1, an, and represent those coefficients either in constant variables or variables known or functions of variables known. So that's our purpose, so that we can use those known functions, variables, or constant to solve the coefficients. Let's just do this step by step. And if the first step, we're gonna solve this a0 here. How could we do that? We implug x equal to c into the equation 1. The left-hand side becomes to fc here because x equal to c. The right-hand side, so those terms, since the second term is all equal to 0 because x equal to c, and c minus c equals to 0. What is left is a0, and remember a0 is what we want to solve. a0 is unknown, and we want to solve a0. So now we know that a0 equal to fc here. The second step to find out a1, we take the first order derivative for both sides of equation 1. So the left-hand side becomes f prime x, which basically is the first order derivative for the function f with respect to x. The second, the right-hand side, it becomes like this. The reason is a0 is a constant. The first order derivative of a constant with respect to x is just equal to 0. The second term is a1 times x minus c here. And here I want to refresh your memory. Z to the power of n, we take the first order derivative with respect to z equals to the power, which is n times z to the power of n minus 1. So for here, when we take the first order derivatives, the power of here is just 1, right? So the first order derivative will be a1 times 1 and times x minus c to the power of 0. Any number or term with the power equals to 0 is just equals to 1. So this is gonna equals to 1, and the second term becomes to a1. The third term, if we take derivatives, a2 times x minus c to the power of 2, a2 is a constant, we just hold it as it is. The power is 2, so it's 2 times x minus c to the power of 2 minus 1. So it's 2 times a1 times x minus c. Next one is a3 x minus c to the power of 3. So we hold this constant as it is. And then times 3 is the power, and times x minus c to the power minus 1. So it's 3 minus 1 is 2. So the first term is 3a3 times x minus c to the power of 2. And keep going. So again, we try this scenario x equals to c. We imply x as c. The left-hand side of the equation is f prime c. The right-hand side of the equation, all those terms equals to 0 as c minus c equals to 0. And the only thing left on the right-hand side of this equation is a1. So we know that a1 equals to f prime c. We basically now solve a0 and a1. Next step, we just keep doing this. We take the second order derivatives on both sides of this equation to get a2. So the second order derivatives, let's just write the first order derivatives here is equals to a1 plus a2 2a2 times x minus c plus 3a3 times x minus c to the power of 2, and keep going. And we take derivatives on both sides of this equation. a1 take derivatives is 0. a2, 2 times a2 take times x minus c take derivatives is just 2 times a2, because here we can, when we take the derivatives, it's a2 times a2 times 1 times x minus c to the power of 0. And this equals to 1. Any term with a power of 0 is just equals to 1. This is equals to 1. So this term, what is left is 2a2. And the third term will be 3a3. The power is 2, so it's 2. X minus c to the power of 1. So it's 3 times 2a3. X minus c to the power of 1. We just ignore it, right? So we keep going. So then we again implant x equals to c in the equation 3. What is left is 2 times a2. And remember, we want to solve a2. So 2 times a2 equals to f2c. And a2 gonna equals to f2c divided by 2. Or the factorial of 2. Factorial of 2 equals to 2 times 1, right? Equals to 2. So this f2c is the second order derivative of fx at x equals to c. So now we solve a2. We can keep going, solve a3. And then again, we just apply the same scenarios, x equal to c here, and we found that 3 times 2 times a3 equals to f3c, and 3 times 2 times 1 times a3 is equal to 3 times 2 times a3, right? And 3 times 2 times 1 equals to factorial of 3. So we found that factorial of 3 times a3 equals to f3c, which means that a3 equals to factorial of f3c divided by factorial of 3. So now we crack a3. So basically we apply this. We just keep finding the next order derivatives of equation 1. And for x an times x minus c to the power of n, we take the nth order derivative. And this basically equals to, the coefficient is the factorial of n times an, and the higher order just equals to 0 when we imply x minus c here. So we can solve that an equals to fnc divided by factorial of n. And after we found out this a0 to an, we imply it back to equation 1, and we get the Taylor series. This is how we get this Taylor series from, from those power series with unknown coefficients. Okay, next I'm gonna show you 2 examples. First, find out the Taylor series of function fx equals to e to x at x equal to 0. So basically c is equal to 0. And remember, the e to x function, no matter how many times we take the derivatives, it's always equals to e to x. So the first order derivative of ex is equal to ex, e to x. The second order is equals to e to x. The nth order is also equals to e to x. This is what you should know to crack this this problem. And if we plug 0, which is c here, so basically it's equals to e to 0, that's equal to 1, e to 0, that's equals to 1, e to 0, that equals to 1. And we can crack this. So fx equals to ex, and it's gonna equals to fc plus f prime c, which this is a1, this is a0, plus a2, this is an here. This is a Taylor's expansion. And f, we plug c here, c equals to 0, is f0 plus f prime 0, and keep going. And f0 here, as we know, f0 is e to 0 is equal to 1. And f prime 0 is also equal to 1. So it's equals to 1 times x minus 0 is equal to x prime x2 0, x2 prime 0 divided by factorial of 2 is 1 divided by 2 times x squared, right? And then finally this one, fn0 is also equal to 0 divided by factorial of n times xn. So basically we found that fx, which is e to x, can be approximated by this power series. This is the first example. The second example is sin x. Fx equals to sin x, sin x. And we also want to find x equals to c. So this x equals to 0, which means that c equals to 0 in our problem. So if fx equals to sin x, then f0, which equals to sin 0, equals to 0. The first order derivative equals to cosine x. And the cosine x, if x equals to 0, is equals to 1. The second order derivative is equal to negative sine x. It's equal to 0, because sine 0 equals to 0. So negative 0 is again 0. And the third order derivative is equal to negative cosine x, which basically is negative cosine 0 is negative 1. And the fourth order is equal to sine x again is equal to 0. So you can see it's a circle, right? So it's 0, 1, 0, negative 1, then 0, 1, 0, negative 1. So the Taylor series for this function at t equal to 1 equals to, this is the Taylor series format, right? So fc, here c equal to 0 is f0, and I just implant 0 as c here. And f0 is 0. The first order derivative of fx at x equal to 0 is cosine 0 is 1. So it's 1 times x minus 0 is equal to x. The second order derivative is equal to 0. So this part is 0. So it's just a 0 here. The fourth one is negative 1, and keep going. So we get rid of those 0 terms because this is 0, this is 0, this is 0. So we found that sin x, this function can be represented as x minus 1 divided by factorial of 3 times x to 3 plus 1 divided by factorial of 5 times x to 5. So this is also a power series. So this is the second example. Back to our bond convexity. So I again copy the Taylor series here. And since bond price is a function of yield, so we label the yield before the change is C, and the yield after change is X. So the bond price before change is Fx, and the bond price after change is before change is Fc, and the bond price after change is Fx. So the change of the yield, which is delta lambda, equals to x minus c here. And the change of bond price delta p is equal to fx minus fc. So use the Taylor's expansion. So fx, this is after change bond price, equals to before change bond price plus the first order derivative with respect to the changes of yield times the changes of yield. So this is delta lambda. And then we just do the derivatives. And plus This is the second order derivatives with respect to the delta lambda and divided by 2, and then keep going. Of course, we do not care the higher orders because we want to do the approximations. So we know that delta p, which is fx minus fc here, equals to those part. So it's we just subtract fc on both sides of this equation. We can get fx minus fc, which is delta p here. So we found that delta p is approximately equals to the first order derivative of function, the bound function p with respect to the yield change times the yield change delta lambda plus 1 divided by 2 times the second order derivatives times delta lambda to the power of 2. And we want to see the percentage change in bond price. So we use delta P, which is change of P, divided by the bond price. So this is what we get from Taylor's expansion, and we divide both sides of this equation by P here. So that's what we get. And we know that this is modified duration times change of yield, and then this is the convexity measure times change of yield to the power of 2. So basically that is a revisit of bond convexity, and for Taylor series, why it is so important. This is because that this is approximate for complicated functions, like the bond price is very complicated. So that's why when we want to do the approximations, we use Taylor expansion and we focus the first 2 terms. Okay, that's basically my video, and thank you very much for watching this video. If you like it, feel free to like the videos, or if you have any comments, feel free to share your opinion in the comments. Thank you very much.